So in this problem, we have a merry-go-round that is in the shape of a disk of mass big M and radius big R. It's supported frictionlessly at its center, and a person of mass little m is standing on its rim. So initially, the whole system of the merry-go-round and the person are rotating with a constant angular velocity of omega naught together. And we're asked to find what the final angular velocity, omega f, is once the person starts walking around the rim in the same direction it's rotating with a relative velocity of v naught relative to the merry-go-round. So since the disk is supported by a frictionless bearing, then angular momentum before and after the person starts moving must be the same, since angular momentum must be conserved. So let's start by calculating the angular momentum before and after the person starts walking on the merry-go-round. So this is the angular momentum before the person starts walking, which we'll call L before. So that's going to be given by the sum of the angular momentum of the disk, which is the merry-go-round, and the person, which we'll treat as a point mass of mass little m. So for a uniform disk of mass big M and radius big R, its moment of inertia is going to be given by 1/2 of big M times big R squared. So its angular momentum is just going to be the moment of inertia times its angular velocity, which is omega naught. Now, the angular momentum of the person, which we're treating as a point mass, is just going to be little m times its distance from the center, which is big R, that squared, times its angular velocity, which is omega naught. Now, if we group like terms, we get that this is going to be equal to big M over 2 plus little m all times big R squared omega naught. Alright, so let's now calculate the angular momentum after the person starts walking on the merry-go-round. So L after is going to be equal to the sum of the angular momentum of the person and the merry-go-round, which is going to be 1/2 big M big R squared. And now the merry-go-round is rotating at a new angular velocity omega f. So we have to multiply that by omega f. And now the person has mass little m, distance big R away, and its new angular velocity is going to be its angular velocity relative to the merry-go-round plus the angular velocity of the merry-go-round relative to the ground observer. So since the person's moving with a relative speed of v naught, its relative angular velocity is just going to be v naught over big R. So its total angular velocity with respect to the ground is going to be omega f plus v naught over big R. So now if we simplify this, we get that L after is just big M over 2 plus little m, all times big R squared omega f plus little m times big R times v naught. And it seems our units check out, so we can move on to the next step of the problem. So since we know that angular momentum is conserved, then L before equals L after. So if we equate the two equations, we get that m over 2 plus little m times big R squared times omega naught is going to be equal to big M over 2 plus little m times big R squared times omega f plus m times big R times v naught. So now if we move the the MR V naught to the other side and isolate for omega F, we get that M over 2 plus, or big M over 2 plus little m times big R squared omega F is just going to be big M over 2 plus little m times big R squared. Let's write it this way. M times big R times V naught minus, had it right the first time. Big M over 2 plus little m times big R squared times omega naught minus m times big R times V naught. Alright, so now if we divide by big M over 2 plus m times R squared, then we're going to get that omega F is going to equal omega naught minus m times big R times V naught over big M over 2 plus little m times big R squared. And that is just going to simplify to omega naught minus V naught over big R all over 1 plus big M over 2 little m. So that's our final answer for the final angular velocity of the merry-go-round once the person starts walking around the room.